Okay, welcome to today's webinar. The topic today is seismic design according to Eurocode 8 in RFEM 6 and RSTAB 9. My name is Andreas Hörold. I'm responsible for marketing and public relations in the Dlubal Software company. For instance, the Dlubal website, the German and English webinars, customer projects, etc. I've been working for the company Dlubal Software for 12 years. And I will be the moderator today. My colleague Stefan will do the presentation and Stine will help with answering the question, but they can introduce themselves.
Yes, hello, my name is Stefan Frenzel. I'm working here at Dlubal also since 12 years. I'm working in the product engineering for the dynamic add-on modules and of course in the customer support. So maybe some of you know me or not. Yeah, okay, I will present today the webinar and Stine, yeah, she will of course answer the questions. So Stine, it's your turn.
Yeah. Hi, from my side, my name is Stine Effler. I'm working for Dlubal since 2018 and I'm responsible for the development of the dynamic add-ons and I'm working in the customer support. I will answer your questions today, so please don't hesitate to ask them.
Okay, thank you for your introduction. Then we can switch off our webcams that the attendees can see the full screen. Okay. You can ask questions via the control panel on the right side of your screen. You can show or hide it with the arrow here and enter a question here. And Stine and I will answer you. If you don't get an answer during the webinar because there are too many, you will get an email afterwards. The other way is to watch the entire webinar and then email your questions to info@dlubal.com. To the agenda today, Stefan will start with this example, a building of concrete and steel, and he will do a model analysis using this example. Then follows the seismic design according to the response spectrum analysis. Then he will show how you can use the results for the structural component design, and he will apply the add-on building model. For example, the shear walls, the forces in shear walls. Okay, then I hand over the screen to Stefan and he can start with the live presentation.
Okay, thank you, Andreas. So yeah, then I think we can start here. Hopefully you see my screen. And okay, you see here a normal concrete structure. So it's for example, it's an office building, and here we have of course a steel frame structure, which is added to this concrete building. And for this one, or for the whole structure, we want to do today a model analysis and of course a response spectrum analysis. You see, we have here, of course, different types of surfaces or of thicknesses of the surfaces. So we have walls with 180 millimeters of thickness. We have here some plates with 300 millimeter of thickness, and of course, different cross-section types. Yeah, so that's a regular building in this case. And at first, I want to show you what we have already or also in the structure. Therefore, we can see here self-weight. Self-weight, there's of course it's the self-weight of the structure, therefore we don't activate here the loads at all, but you can also activate these loads. Therefore we have here an option for self-weight. We can activate this or not. It's just a structural self-weight. Another load case is here, of course, an additional self-weight, so which comes of course for the concrete here in this case, or for the concrete surfaces. There we have an additional self-weight. And of course, here some imposed load cases for the roof, for the second floor, for the first floor. These loads we want to use also then in the model analysis. And of course, you see here a snow load, which looks empty, okay. And yeah, we can create a snow load, that's no problem. And of course, a wind load. For the wind load, you see that we have here already also like a surface load, yeah, which is applied here on this opening. So in RFEM6, we are able to apply also loads on such openings, and therefore we have here a special surface type, which is called load transfer surface. So this load transfer surface is able to transfer the surface load to some elements. For example, I activate this one, or I will have a look in it, and here I can see, okay, I will try to transfer the load to these lines, yeah, that are the lines, of course, from the floors, and therefore it's possible to use such a load transfer surface. Here, of course, we have a wind load case also in the other direction. These wind load cases we want to use afterwards to compare the results between the earthquake calculation and, of course, the wind calculation. And maybe we can, or we will be able to use the wind calculation for the checks or for the design checks afterwards. Okay, I will deactivate the load transfer surface here in the first step because we don't need it directly. And then, of course, I saw that we don't have a snow load, so we want to create the first a snow load. Here, we just type in 0.68 kilonewtons per square meter as load. And of course, it should be assigned to this surface. Oh, wait, I have to delete this at first, and then I can choose it. It's surface 25, and therefore I will have also now my snow loads. So the next step is that we want to do, of course, at first the model analysis for the structure. And to do this, or if we want to do this, we have to activate the add-on module model analysis. We can do this really easy because we just have to go here in the navigator data, and here we have basic settings, and in the basic settings we are able to choose the add-ons what we want to use here in the program. Oh, I have to deactivate the first steel design because we don't need it at first. And here we have the dynamic analysis part. You see that we have here now model analysis and response spectrum analysis for RFEM6, and you see here some grayed out add-ons. These add-ons will come in the future, so yeah, they're not already finished, and therefore we just grayed out them. So that's just for you that you know what will come in the future. Our first step should be that we want to do a model analysis. So we have to activate the add-on model analysis, and then we can go through the standards, because here the standards are really important for us, because at first we have to classify or to classify the weights for the earthquake or for the model analysis, and then we have, of course, to classify the dynamic analysis settings. So which response spectrum or which additional or which national annex we want to use, for example, for the Eurocode. Here you are also able to choose, of course, another dynamic design analysis. So you can use, of course, the American standard, or you can also use some other standards, what you want to use. Sometimes it could be that we have new national annexes from a new year. So like here from 2021, last year for Germany. Is it also possible to say, okay, we want to see also the old standards here, for example, 2011, yeah, and that's you can do here with this button. In our case, we want to work, of course, with the national annex from 2021, and that should be all here at first what we want or what we have to do. So we activated now our add-on module, and the next step is that we have, of course, to create here the calculation of the model, or that we have to create the eigenvalue calculation. So how we can do this? Maybe you know it from the old RFEM5, you had to open an additional module where you have to give in the input data. Here in RFEM6, we work just global, so that means we don't have to create, or don't have to open an add-on module, so we can do it here directly in our navigator. Therefore, we have to create here at first a new load case, and this new load case has a category. And for this category of this load case, the analysis type is standardized as a static analysis. Here in our case, we want to use, of course, a model analysis, because we have now here a model analysis, because we activated the model analysis in the add-on modules. And therefore, we are able to choose, of course, an analyzer setting for our model analysis, and we are able to import masses from a load case or from a load combination. At first here, we want to change the model analyzer settings. Therefore, we can use this button here, the edit button. And for the edit button, we can say, okay, we want to have just the directions X and Y, because we want to do afterwards a response spectrum analysis. And for a response spectrum analysis, we want to use just the X and Y direction for the mathematic settings, and of course for the eigenvalues. The number of modes should be here 30 at first, because I know the structure, that's why I use here 30. And of course, the other settings are not so important for us. So the mass conversation type, it's clear normally. You need just the Z components of the loads, and we don't want to neglect any mass. So we want to use all masses of the structure in this calculation. Then we can say here, okay. And now we are ready with the model analysis settings. The next step is that we have to import our masses from a load case, or that we will have to import completely masses for the calculation of the eigenvalues. So therefore, we have, of course, the option to choose here a load case or to use a load combination. Yeah? But in our case, that is it not enough, because we need now, of course, the loads or the masses according to our design code Eurocode 8. And we can now, or we are able here in RFEM 6 to create this design situation. And therefore, we just have to switch here to the next tab. It's called also design situation. And here we can say, okay, I can delete these ones at first, we don't need. Sorry for this. So we create a new design situation. And in this design situation, we are able to choose here seismic mass combination. That means for us, the program can use now from your design code the formulas, like here for the Eurocode 8, and can, of course, create a load combination according to this design situation, what we can use then afterwards in our load case or in our model analysis setting. So here we can click on close. That's now at first all for us, because we can now go completely here to load combination, and the program will create directly a load combination for our model analysis. If we switch here to assignment, we can see, okay, here the value 0.3 is used. Of course, the snow load, we have to use the snow load in Germany. I think if you use the normal Eurocode, you don't have to use it, so without a national annex. But of course, that depends, of course, on the national annexes for each country. Here you see that we have now a FC value and a phi value, yeah. And these values, of course, are important, because it could be that these values are smaller or bigger. So, but how you can control this, that's also really easy. You can go back to the load cases, and if you are here in the load cases and in your imposed load cases, then we have, of course, an additional setting, which just comes if you activate the add-on model analysis. And for this additional setting, you can switch between roofs and other floors. So, and that means if you use, for example, a roof, then this psi value is another value than for other floors. And that means that that the loads which you import could be smaller or could be bigger. Yeah. And here you see that we have, of course, the additional setting for our load for the roof. Of course, we say that's the roof, yeah. And for the second floor and for the first floor is another floor. If you use here, of course, also the normal standard Eurocode without national annex, you have here also these values and have also some different values for that. So that's just in Germany that you have here, of course, roofs or other floors. Okay, then we can go back here to our load case, and we create before our load combination. It was made automatically. And here's it now possible to choose, of course, our load combination. It's load combination number 1. And for this load combination, or we want to use this load combination for the model analysis. It means all loads which are in this load combination are calculated as masses, and just the Z direction is used of these masses. So if you have, for example, wind loads are never considered in such a calculation because they are horizontal loads and they don't have parts which are working in that direction. Okay, then we can click here on calculate all. The program now calculates or meshes at first the structure. Then you see that the program will calculate all load cases. Here we have a multi-core calculation. It means in my case I have 8 cores, 8 CPU cores, and these 8 CPU cores calculate all load cases in one way. Okay, the result looks like this. So at first we have here now the result in our navigator results. We see here our national frequency from 1st to the 31, and of course I have here the option to have a look on the mode shape and of course on the masses. You see here in the graphic, if I rotate it a little bit, that I have, for example, now here my biggest value for the deformation, and that means if I have a look here in the table, I have here many frequencies, but the important thing for an earthquake calculation is normally the effective modal masses or the effective modal mass factor. And you see that the first 7 eigenvalues are not so important for me. Yeah? That are just local eigenvalues which are here in the steel structure. For me, the first important value is here the 8th eigenvalue, and the other ones, of course. And it means for me, I need here nearly 30 eigenvalues to reach the maximum of 96 or 95% in X or Y direction. And that means for me, okay, I have to calculate 30 eigenvalues. Maybe it's not so easy for bigger structures, because if you have to calculate more eigenvalues, then the calculation takes, of course, longer, and the performance is not so nice. For this case, normally it could be, or it could be also that you don't reach the 90%. Yeah, could be okay. You calculate 20 eigenvalues and you don't reach the 90%, and that means for you that you have to increase the values and you have to calculate more eigenvalues. But in our case, I want to show you what we can do if we have such a problem. So here in this example, we have 30 eigenvalues, but normally I want to calculate less than 30 eigenvalues. And therefore we go back here to the load cases, go on edit, and here I just copy my load case, and it means, okay, I got a complete copy of the load case. So it's a model analysis, it's the same loads are imported, yeah, and the model analysis settings are also the same. But in this case, I will create, of course, a new model analysis setting, and here I just want to calculate 10 eigenvalues, just in X, Y, and Z direction. So that's nearly the same option like I had before with the 30 eigenvalues. And we know that the 8th, the 9th, and the 10th eigenvalue could be important for us, but I never reached the 90% with these 3 eigenvalues. So, and therefore we have here now the option in the settings, so to neglect masses. Here we have, of course, 3 different types. The first one is, of course, no neglection. We don't want to neglect any masses in the structure. Then we can, of course, neglect all masses in fixed nodes or line supports. Yeah, but here be careful, just in nodal loads, and not just in nodal and in line supports, not in surface supports. Yeah, and then we have the last option, user defined. And user defined is the one what we want to use. If you activate user defined, you will get here a new tab which is called neglect masses. And for these neglect masses, we choose now, of course, our members from the steel structure, because the masses of the structure are so small that they are normally not so important for our calculation, because the concrete building gets, of course, higher values, and therefore it's important to consider the concrete structure but not the steel structure. And then we get, of course, an object list, and for this object list I'm able to choose, of course, just directly here the members. So I want to have this member, and this member also. Can say here okay, click here also on okay, and now of course I can calculate my load case number 10. Now the important thing comes, of course, because now we will have a look on the calculation results, and we see, okay, we have 98% in each direction now, and we did this with just 10 eigenvalues. So that means for me, this is of course more effective for me, because I don't need to calculate 30 eigenvalues or 50 eigenvalues or whatever. And here, of course, I see directly, okay, my first eigenvalue is just on the concrete building, the second one also, and my steel structure don't get any eigenvalue. I get here, of course, deformations, but these deformations are just coming from the concrete building, because yeah, it's a hinged structure, yeah, a hinged steel structure, which of course gets the same deformation like this wall here at the end, yeah. But to have a look and to control it, you are able to have a look on the masses here in the program. If you activate these masses, then you can have a look here. For example, I will go here in this view. Then you see that the program will create, of course, a mass ball. So we call it mass balls in each FE mesh element. And of course, for the members, we don't have any masses, so we have always a 0 value. That means for us, these members are completely not used for the calculation. So the masses of these members is not used for the calculation, but the stiffness. And it means for us that these members don't get an eigenvalue, a local one. So we have just now global eigenvalues for our structure, and that's the important thing here in this case. Another thing is that you are also able, if you have a look on the mode shapes, that you are also able to scale the mode shapes. Yeah, maybe scaling of the mode shapes could be important for you if it's some technical work or something like this, and therefore you are able to change here the scaling of the mode shapes. In RFEM 5, in the add-on, was it like this, that you had to do it in the input data and you had to recalculate it afterwards, and that was normally not necessary, and that's why we changed it here directly and bring or created this option here in the results. Yeah, and here you are able, of course, to change the scaling. Yeah, if you change the scaling, of course, the table is also changed. Normally we use here always U as 1, and that's okay for us, because here we get the highest deformation, and the highest deformation is always 1, and the rest of the structure gets, of course, then the other values. Okay, that was the model analysis of our structure. I think you saw here at first the calculation of it, and of course the input data, and then we want to come to our next step, because with our model analysis, what we did now here in the load case number 10, what is our important one, we can go here back in the base data and can of course activate that on module response spectrum analysis. The response spectrum analysis, maybe you know it from RFEM 5, there we had an add-on module which was called equivalent loads, and the response spectrum analysis is nearly the same, but here in the response spectrum analysis, we don't give you the loads at the end, so we give you directly the results at the end. And that is here, of course, the new thing, because in this case, you save a lot of performance of the program, because you don't have to show the loads on each FE mesh point. So you get directly the internal forces, and you will be also able to do an analysis with this internal forces directly. So here it's activated. The standards are of course the same. So that means we will use our national annex Eurocode 8 from Germany, and that's all at first. And here we do it like for the model analysis. So here we have to create at first a new load case. And in this load case, we don't want to do a static analysis or a model analysis. We want to do here a response spectrum analysis. With this response spectrum analysis, we are able to use, of course, or to import the load case number 9 or load case number 10. So we are able to import our model analysis. In our case, we want to import, of course, the load case number 10, because here we got our 98% of the equivalent load factors. And that would be nice for us to use it, because here we had also just 10 eigenvalues. So next step is, of course, here we have to create our response spectra. Oh, yeah, I will show you at first the response spectra. So to create a response spectra, of course, you have just to activate the direction. The program will then automatically create a response spectra according to Eurocode 8. But you are also able to change this. Yeah. So what values you have to put in, that's also the important thing. And therefore, I want to show you our web page. On our web page, you can find under solutions via snow load, wind speed, and seismic load maps the correct value for you. Yeah, what you want to use. In our case, we go at first on seismic, because we need the values for the seismic calculation. And then we want to use, of course, the German annex. It's Eurocode 8 part 1. And now you see here, of course, the whole map for the earthquake loads in Germany. And of course, you can enter a location. I will enter here Leipzig, because I do my webinar here in Leipzig, and I think it could be good, because here we are on the border to a seismic zone, but it's not a real seismic zone. Yeah, this map looks stranger than it is. And of course, here we have now our reference peak ground acceleration, which is here with a value of 0.169 meters per square second. This is a small value. If you go to other countries, of course, you get much higher values. Yeah. So in our case, okay, we want to use this value. Then we can go back to our RFEM, and we just have to type it in 0.169, and that's all at first. Yeah. So our ground type, of course, should be AR. Here it's also could be also possible to change the ground type. You can find it here directly also if you go the subsoil class. Yeah. And for the subsoil class STR, yeah, we have normally nothing like this, NA. So I took R in this case, it's okay. And that's all. Okay, that should be our setting for the standard. Yeah, you are also able to change the behavior factor or whatever. That depends, of course, on your structure. In our case, we take here the standard values of 1.5. That's okay for us, and then we can click here on OK. If you have other changes, like you want to scale up the whole period or the whole diagram, then you can here also scale up, yeah, if you need this. The next step is that we can go to the selection of modes, and here you see the program now has selected all 10 eigenvalues, and we have 98 or 99% in each direction. The Eurocode says normally that you just need 90%, and at least you need, of course, all eigenvalues which have a higher effective modal mass factor than 5% in this case. And that's what we can do here also, just by clicking on deselect modes and use this value. So we want to use the 5% value. The program is already also over 90% in some of it, yeah. But we just need 4 eigenvalues for that. and that's the important thing. So that's also a performance point, just to use the eigenvalues which you need and not all eigenvalues. Then we can go back on main, and here in the main tab we have to use, of course, our spectral analysis settings, or we have to change them. Therefore we go on edit, and in the edit button you will come to the settings, and the settings are changeable, of course. The first one is, of course, the combination rule for the periodic response. So here you are able to use the SRSS rule, the CQC rule, or the absolute sum rule. So the Eurocode says here in this case that you have to use the SRSS rule or the CQC rule. In some cases you have, of course, to use the CQC rule, but it depends on the values or on the difference between the eigenvalues, between two eigenvalues. Yeah, is this difference really small? You have to use the CQC rule. Is the difference high enough? You can use the SRSS rule. That's, of course, what we want to do. We want to use, or we want to save, of course, all results of the selected modes. That means the program should save these results, and because otherwise the program will just give the end result of it, and that's maybe not so good for us, because we want to show, or we want to know everything, and we want to use also the sub results for that. The next thing is, if we have combined our directions in X and Y direction with the SRSS rule, for example, here we have to combine then the X with the Y direction, and therefore the Eurocode gives us also some options. Here we have at first the SRSS rule again, which is not so effective, I would say, and then we have, of course, the scaled sum. If you activate the scaled sum, then the program will take automatically the 130% rule. But here you are able also to change the 30%, for example, to 40% or whatever what you need. It's not according directly to a standard. It's according to your standard or to your behavior in this case. Yeah. Okay, that's all for this, and then we can click here on OK. For such a response spectrum analysis, the Eurocode or other design codes also say that you have to consider the accidental torsion. This accidental torsion, you are also able to activate this here directly, and therefore you just have to click here on. You have just to click it on, and the program says, okay, 5% for each direction. Then the program will give you here the building length, or you can also use it, or you can type it in manually if you want. And so the accidental torsion is completely considered in the calculation. So how the accidental torsion works is really easy, because internally, of course, the program will create also FE loads or loads on each FE element. And the accidental torsion is considered like this, that we create, of course, a small moment by the eccentricity and the force from the earthquake on each FE mesh element, and bring a small moment around the global Z axis on it. And that's the accidental torsion. This one is, of course, completely done automatically. You don't have to consider this. So next step is we calculate all. Now the program, you see, will calculate sub-results for load case number 11. It's because that is also a change in the program, or a change in the program from RFEM 5 to RFEM 6. Because here in RFEM 6, we are able to save sub-results for in load cases. So we don't need load case, because in RFEM 5, we had just load cases, and we had for each load case one result. And here in RFEM 6, we can save more than one result in a load case. And that's, of course, a big effort, because we don't need result combinations at the end, and we are a little bit smarter in this case. So the program calculates now load case number 11. And of course, I have here an envelope, the scale sum envelope here. Then I have here the 130% rule, the 30-100% rule. Maybe you know it from RFEM 5. You got a result combination for the X direction, a result combination for the Y direction, result combination 130 and 30-100, and no scale sum because you had to do it at the end manually. Here in RFEM 6, we have it, of course, exactly for all results, and that's of course the effort here. But you are also able to have a look here in the results directly. You can, of course, look in the internal forces, for example, the normal forces, and you can also have a look at the end for the scale sum. So that was, in this case, at first the response spectrum analysis. And now we want to have a look, okay, how we have normally now, or we need normally now, a combination because we have just a response spectrum analysis, but we have to combine it normally with a self-weight and with some imposed load cases. And here in RFEM 6, we are able to do this also automatically. And how to do this automatically is also new, because in RFEM 5 you had to do this manually. And here in RFEM 6, we go back in the load cases and we create here a new design situation. That's the easiest way normally. In this case, we want to have a seismic design situation, ULS, ultimate limit state in this case. Oh, wait, it was my fault. Edit. Design situation. We need a new design situation and not the old one. If we change the old one, then the results are gone away. So we take here the ULS at first. And for this design situation, we have to combine these loads now with the result combination. That means we can just add the results because our sub results are already there in the load case, and we just want to add them together at the end. So if I go now to the result combination, you see the program creates here the result combination. I can have a look on the envelope. And then I see, okay, my load case 1, the second one is in, my imposed load cases are in, the snow load is in, but the wind load is not considered, yeah. And my load case number 11 is also in, and here the scale sum of the envelope is used. Here I'm also able to change it. Here I can also use the 130% rule, or I can use just the X direction if I want to have this. This sub results tab here is just activated if you are here in the base settings, or if you activated the sub results here in the base settings. If you deactivate here the sub results, then here in the result combination is it not possible to change this, and so the maximum result is always used. Yeah, that's just as an info for you, that you know that you are also able to change this. So now we have here our results for this. Of course, we can now calculate this. It should be no problem. And of course, we have now our result combination number 1 with the complete results for the seismic calculation. So, but now I already not know what I have to do here with these results. Do I need to use these results for the design or not? Yeah. And normally in Germany, or maybe also in other countries, is like this, that you have to compare these results with your normal ultimate limit state calculation. And therefore we go already also on edit and create here a new design situation and say, okay, my new design situation should be this one here, my ultimate limit state. Yeah. And afterwards, I want to compare these two ones with the base here. So, and therefore we go, of course, on OK, result combination we don't need directly, but we have to calculate it all. You see that the program now calculates all load combinations here, 8 load combinations at one time. Then I think it will take some seconds, and because the program has to calculate now here 100 load combinations. And that will take some seconds. But here maybe I can say also something to this. Here the program will calculate, of course, now all load combinations, and you saw that these load combinations are really, or that they are created really fast, yeah. So that's also a big effort of RFEM 6 here in this case, because you don't have to wait so much time for that. Here in this case, the program will calculate, of course, 8 combinations at one time. Problem is here, of course, that I have load increments in it. That could be that it takes a little bit longer, but that depends always on the structure, because you have some diagonal members which could fail, yeah, and that could be here the problem. But we will wait a second, and then hopefully the program will give us a result. Of course, now we have the result for that. And of course, here we can have a look now on the results, but I have already the same problem like before. I did here my static analysis. And of course, I did here my design situation. I have here also my design situation for the whole structure, but I'm not sure, okay, what's with my base shear in the structure? Is my base shear too small, or is my base shear for the ULS bigger than for my earthquake analysis? And that's now my issue. And therefore we have here a new add-on, because otherwise in RFEM 5 or here in RFEM 6, it's also possible to use a result beam. Yeah, that means I have to create here a beam. Yeah, that's added lines. And here, of course, I'm able to create here a member. And here I'm also able to say, okay, a result beam. Here I can, of course, integrate all surface and all members of the structure to member internal forces. And then I can, of course, compare the shear force of this member with these two result combinations or design situations. But in our case today, we want to do it in a little bit other way, because here we have in the base settings also a new add-on, which is called building model. And for this building model here, is it possible now to give in or to calculate the base shear directly? So I activated now the building model, and the building model, you can find it here at the end. That means here I have to create stories now, because I need some points where I need the base shear, of course. And therefore I can go here on new building or a new story. That means the program will open here, of course, a small window. Here I can have also a look on my structure, and here I can say, okay, my first floor is 350 high, and of course we don't need a rigid diaphragm, because we have all surfaces in, or all floors in, and therefore we don't need the story slab stiffness. The story slab stiffness is just normally if you don't activate your real floors, because it's also possible just to calculate the winds and the walls and of course the columns, and therefore you can use this. Here I want to create also 2 other floors. You saw that I just clicked here on create new higher building story, and the height of course is 3.5 meters, and that is my difference in Z direction. And of course we have already the same value there. Then we can click on OK. And now, of course, I see here my stories, but where can I find my results for that? And that's now the important thing, because you are able now here to go here in the static analysis, for example, and you will get here, of course, a new overview results by the stories. The results by the stories for my ULS, you can find in here, yeah. That means my maximum base shear in X direction, in global X direction is 328 and 240 in the Y direction, yeah. And now I can also have a look on my seismic design situation. And here I have now 275 and 183, yeah. That means these 2 values are smaller than my ULS calculation. And then I know, okay, if these values are smaller, I don't have to consider or I don't have to consider the earthquake for the design according to any standard, for example, according to Eurocode 3 or according to the Eurocode 2 for the concrete. So I can use my normal loads and don't have to consider the earthquake calculation in it. What's also important here is that you have for this building model also the option to have a look on the displacement for the interstory drift. So that is also important because we want to bring in the future an add-on module which is called pushover analysis, and therefore you need, of course, the interstory drift. And here's it also important to know what to do by hand calculation now, but maybe in future we can do it also automatically to calculate if you have to consider the second order in earthquake analysis or not. Yeah, that's also some point. That is also a point for that. So the building model will of course expand in the future and will of course get other options for that. But here that are the first things what we have in the building model. You see also that you have a center of the mass and the rigidity, so you know the mass in each floor. That's also an important thing. And of course, the forces in the shear walls, because the program is able to create internally a result beam for each wall in the structure and to calculate the shear force for that. And with the shear force, you can do easily a design for the shear wall, or you can easily do a shear wall design at the end. Yeah. Okay, that was my presentation for today. Andreas, are you ready?
Yes, I'm ready. Thank you for this nice presentation. Yeah, for all attendees, if it was too quickly for you, that's no problem. You can use our recording. We record every webinar, and you can use also the model. We provide a model on our website for download. I would like to show you where you can find it. Just a moment. I have to share my screen. Okay, on our website, dlubal.com, you can find the webinars under news and events. Here below, the webinars. Yeah, as I said, we record all our webinars. You can search for any webinars by scrolling down or enter full text search. That's today's webinar. And in the next days, you will find the recording here in the middle, and you can already find the model to download here, and you can go through the webinar step by step if you want. If you don't have got our RFEM 6 or RSTAB 9, you can download our free trial version. Here above, you can find the free trial version of RFEM 6 and RSTAB 9. Both programs contain all add-ons, and you can test it for 90 days. Okay, yeah, that should be all also from my side. Maybe a last hint: when you leave the webinar, where is a small survey? Yeah, you can score us. Just note that the worst score is 1 and the best score is 5. And you can answer some questions. For example, if you have wishes for future webinars, but if you haven't, you can enter a minus or something, or a sign like that. Yeah, okay. Then thanks to Stefan again for his nice presentation. Thanks to Stine for answering the question. Yeah, and thank you again for your attendance, and have a nice day. Bye-bye.